Hello class, this is Mr. Roberts, Shasta High School. Uh, this is a quick talk through of the pretest that we handed out on, Tuesday of this week. We started Chapter 2, but the test for Chapter 1 is going to be this Friday, and I'm just going to go through the solutions for this test. The answer key is posted on Aries if you want to just look at the answer key, but this is me kind of rambling through them. So the first question asks us to write some particular numbers in something called roster notation. One of the important things here is that we're using the word between. When we say between, we're not including the endpoints. So some of the values are not going to be included, just the ones between 3 and 7. So write the natural numbers between 3 and 7. This set of numbers is very specific, and I hope that you have an idea of what that means. I open these, the braces. The first number, natural number that's between 3 and 7 is 4, and then we have the 5, and then we have the 6. So notice I'm not including the endpoints at 3 and 7. Question 2 says, use set builder notation. Use set builder and interval notation to represent the numbers indicated on the number line. So if I'm looking at these, I can see that this is starting at -3, but it's not including that point. This is right here at 2, and it's including the point. So please know the difference between whether or not a point is included or excluded. In set builder notation, it would look like this. We would say all, and I'm not very good at that. I need to practice that. All values of x such that, and this is between, so I can use and, or I can join it into a compound inequality here. So I'm going to go with this. X's are less than, and they can also equal the number 2. So all values of x that are less than or equal to -2, but they also must be strictly greater than -3. So these are all the values of x that are in that range. You can see I'm including the negative. I'm not including this in -3, but I am including the +2. And if I want, I could specify and the x's are elements of the real numbers set. And I might include that, just I don't really need to include it, but you can see right here it's including everything. They're not just integers or natural numbers, it's all of the numbers in between. Interval notation, again, we are not including this endpoint, so I use the curved parenthesis 2, and then we're going all the way. No, it's not 2, it's starting at -3, sorry. So it's curved and we're starting at -3, and we're going all the way up to and including this endpoint at 2. So here's our set builder notation and our interval notation. Next question. It says, we have a set of numbers here. It says, order the following numbers from least to greatest. Write one number per box and indicate the set or sets of numbers that each value belongs to in the matching box. There's actually, I have the last items backwards on my answer key, and I don't know what I was thinking, because clearly pi is less than 5.12. If I look at these, I have a couple negative numbers, right? This is 2 1/3, and this is -4. So this is the smallest of all of them. So I'm going to go ahead and begin by writing that one. We'll just need to grab a pen. So my first number is negative the square root of 16, which is just equal to 4. The next number that I have is -7/3. After that, we have the number -1. The next largest number that we have here is pi, and the largest number in this set is 5.12 repeated. In terms of sets, -√16 is a member of the real number set. In fact, all of these are real numbers, right? I'm just going to go ahead and they're all real numbers, and real numbers. Negative root 16 is also a rational number, because I can write it as a ratio of two numbers, and it's also an integer, right? Because it is, after all, just negative 4. Don't be confused by this radical symbol, right? Remember, this is just root 16, which is 4. It's not the square root of 2 or the square root of 5. Negative 7/3 is a real number, and it's also a rational number, because I can write it as a ratio of two numbers. Negative 1 is a real number. It's also a rational number, because I can write it, for example, as negative 5/5. I can write it as the ratio of two numbers. And it's also a member of the integers, sets of integers. Pi is a real number, but it's also irrational. That's the only irrational number here. And the last number I have is 5.12, which is a real number. And because this is repeating, I can write this as a ratio of two numbers. So it is also a rational number. The next set of questions asks me to identify the property of real numbers that's demonstrated in each situation. So the first one is an example of the distributive property. And we don't, what we're distributing doesn't have to be, in front or anything, but I'm distributing y to both the 3x and plus 2. The next property here we have 5 times 3 times 2 equals 5 times 3 times 2. And this is just an example of the associative property. I'm changing the association that I see here. And of course, there's no change in value. I can look at this as 5 times 6, which is 30, which is the same thing as 15 times 2. 5 times 6 and 15 times 2 are both 30. The next problem, when I look at it, I've got a 5, 6, and a b, and I have a 6 and a 5 and a b. And what I've done here is I've commuted the 6 and the, let's see, what have I changed? The 6 and the 5 have switched places. This is our commutative property. And finally, part D, 4D, is the multiplicative identity. And I'm glad that we had our conversation about these properties in class today when we talked about properties of equality. Number 5, what is the multiplicative inverse of 3/4? And that's quite simply 4/3. And of course we know this is true because anytime you take anytime you take a number, really? I don't want to change time. Anytime you take a number, and like for example 3/4, and you multiply that by its multiplicative identity, you should always get the number 1. I'm sorry, by its multiplicative inverse, not the multiplicative identity. The property of multiplicative identity is any number times 1 equals itself. Here, multiplicative inverse, what undoes multiplication? Multiplication by the inverse will undo it. Moving along to question 6. 6 has several parts. It says simplify each expression involving the square roots, and there's 5 of these. The first one, I'm going to rewrite this as 2 times 18. 18 is of course 2 times 9. I'm going to go ahead and write this out rather laboriously as the square root of 2 times the square root of 233. 2 times 3 times 3. The reason why I do that is when I look at it, I can see I have pairs of roots that are together. Of course, we can combine the product of individual roots, right? I can combine the product of this root and this root into one root. So I can write this as 2233. And if I look at these, The square root of 2, which is the square root of 4, is a perfect square, and the square root of 3 is a perfect square. And they are respectively 2 and 3. So my answer is 6. B, simplify this. I have a radical in my denominator. I don't have any perfect squares in either one of the radicals, but there is a radical in this denominator, so I'm going to multiply this fraction by the number 1, and I pick a special form of the number 1. I pick the value of number 1 that will rationalize my denominator, because that's one of the things that's important in simplified radical form. We do not leave radicals in our denominator. My denominator now is root 3, and the square root of 3 times the square root of 3 is equal to 3. And my numerator is 2 times the square root of 6. And we're going to leave it right there because there's no common factors between those two. C, you can do several ways. I think probably one of the easiest things to see is that there's something going on with the 42 and the 14, and there's going to be some common factors there. Let me write this out. This is going to be 2 times the square root of 42, of course, is 6 times 7, and 6 I will write this way. So there's 42. And now my denominator is going to be the square root of 2 times 7. So when I look at this, right, these are all factors. And I know that I can take a root, this root of 237, and I can turn them into individual roots. So this is root 2 times root 3 times root 7. I can do the same thing down here, root 2 times root 7. What I'm going to do is I'm going to cancel these common factors, right? There's a common root of 2 in the numerator and denominator, and a common root of 7 in both numerator and denominator. When I'm finished with that, I'm left with 2 times the square root of 3. Part D, let's see, both of these have some perfect squares in them. In fact, the square root of 45 is, of course, 9 times 5. So I'm going to look at this as the 9, which is root 3, and then a 5. So I've got a root 3 times a root 3 times a 5. And I'm adding that to the square root of 20. 20 is 4 times 5, or 225. I just like writing them in their completely factored form. When I look at these, I can see here I have a pair of identical factors, a pair of identical things inside of my inside of my square root. So when I take the square root of 3, I'm left with a 3, and still there's a root 5 inside. And here I have a 2, square root of 2, or square root of 4 is 2, and I have a root 5 inside. If I combine these, I can combine these because they're both root 5s. These are treated just like variable expressions. I have 3 root 5s and 2 more root 5s. When I combine those, that's 5 of these things I call root 5s. And the last part here is E. And E, we talked about this a lot in class, and quite a few of you had 5 root 7 as your answer. When you do that, realize what you're doing is you're attempting to, cancel common terms. Be very careful. If I look at 3 plus 2, and I divide this whole thing by 2, many of you will try to convince me that you've seen this before, Mr. Roberts. Trust me, you can, just magically get rid of the 2's. Remember what this means, right? My numerator is the number 5, and my denominator is the number 2. If I simplify that, that's 5/2, or 2.5. Now, if you come in and you're like, hey, I'm just going to get rid of those, all of a sudden you're calling this the number 3. And it is not 3. 3 is clearly not the same thing as 2.5. So, however, what you have seen, if you look at this, if I had 3 times 2 over 2, of course 3 times 2 is the number 6 over 2. 6 over 2 is the number 3. So you can see, in this case, right, I can begin by eliminating a common factor. Remember, factors are things that are multiplied together to produce a product. So I have here 2 factors, 3 and 2, as opposed to here I have 2 terms, one of the terms is the number 3 and the other term is the number 2. So we can cancel common factors but not common terms. That brings us to part E. We can't just come along here and cancel out these root 5. What we've got to do instead is we've got to multiply this by the number 1. Again, the reason why I'm picking this form of the number 1 is I know that it's going to allow me to rationalize this denominator. A point of something to notice, though, is that I am literally multiplying this numerator, root 5, times this entire numerator. So when I do that, I have to be very careful and make sure I distribute this root 5 to both of these terms. So my numerator now will become 5 times the square root of 35. And I'm going to be adding to that root 5 times root 5. So again, I'm multiplying both of these, right? Root 5 times 5 root 7 and root 5 times root 5. And when I multiply root 5 times root 5, I get the square root of 25, which is 5. So I'm going to write that. And my denominator now is 5 also. Now, when I'm here, right, I see there's 5s all over the place. And, you know, many of us may be tempted to just try and cancel these. We can't do that. However, in my numerator, there is a common factor. I have two terms, this term and the second term, and they have a common factor of 5. So I'm going to factor out that common factor of 5. My numerator then would become 5 times the quantity of the square root of 35 plus a 1. And again, take a look at this, right? If I multiply 5 times root 35, I get exactly this. And if I multiply 5 times 1, I get exactly 5. In my denominator, I have this 5 that's still sitting down here. Now, please contrast over here, right? I have a common factor of 2 here, and I have a common factor of 5. Big picture, I have 5 times something. I don't care what this something is. 5 times something is what I care. These are factors, and I can eliminate them. So my final answer here is the square root of 35 plus the number 1. Well, that's that. Let's see. I can scroll this way for some reason. Okay. All right, number 7. Evaluate each expression if x is 3 and y is the number negative 2. Okay, so grab my pen again. So I'm going to go ahead and use some parentheses here. It just helps me avoid possible mistakes in the future, especially as these expressions I'm evaluating become, potentially more complex. So I know that x is 3, so I'm going to plug a 3 in for the x. Then I have plus 3 times an x, which is 3, and then times a y, which is negative 2. And I'm going to subtract from that 2 times y, which is negative 2. So you can see I have the 3, and then plus 3 times negative 2, and then minus a 2 times a negative 2. Again, writing these things out just make it so that much easier for my brain to keep track of what's going on. And the more I write out like this, the less I have to worry about, dropping things or losing things or forgetting things. If I do some arithmetic here, this becomes 3 plus, 3 times 3 is 9 times negative 2 would be 3 plus a negative 18. And then I have a negative 2 times a negative 2, which is going to be a positive 4. So if I look at my positive values, I've got 3 and 4, which is 7. And I'm going to take 7 and subtract 18 from it, and 7 minus 18 is the number negative 11. So that's part A. Part B, same thing. I'm going to substitute in here. I'm going to go ahead and use parentheses. Y is negative 2. I'm going to square that value, plus 2 raised to the power of, let's see, x is 3 minus 1. And then I'm going to be adding 10 to that result. Negative 2 squared is a positive 4. And then I have plus 3. This will be squared as well because 3 minus 1 is 2. So 2 squared is another 4. And then finally, I'm going to be adding the 10. Well, that looks like 8 plus 10, so my answer is 18. Part C. Same values for x and y. X is 3, so I'm going to have a 3. And then I'm going to have times a negative 2 for y, and I'm going to square that negative 2, plus 4 times 3 for x, and then plus a negative 2 for the y. So simplifying this, this is 3 times negative 2 squared. Negative 2 squared is positive 4, so this is 3 times 4, or 12. And then I have another 3 times 4, which is 12. And then finally, I have a minus 2. I don't know how that got down there. Let's see. Minus 2. So when I look at this, I've got 12 plus 12 is 24, minus 2 looks like 22. Now we're on to question 8. 8 says, simplify the following expressions. Okay. So I look at this and, I see that there are some things trapped inside of parentheses, and I can use the distributive property of real numbers to eliminate those parentheses. So I'm going to do that. So using the distributive property, this first term becomes 6 times x plus 3 times 5 is 15. And then I have a minus 4x, and then I have a plus 7x plus a 7. If I combine like terms, then you can see I've got 6 x's, I've got 7 x's, and I've got negative 4 x's. So combining the 6 and negative 4, that's negative 2. And when I take negative 2 and combine that with a when I take negative 2 and combine that with a, that's going to be positive 2. 6x minus 4 is 2x, and 2x plus 7x is going to be a 9x total. And then I have a 15 plus 7, which is the number 22. So this is 9x plus 22. Part B, I have a fraction. The numerator has several factors that are all being raised to the negative 1 power, and the denominator has just a plain old x to the third. I'm going to go ahead and, whoops, and there's lots of ways we could go with this, but I'm going to go ahead and get rid of this exponent. I'm going to make this a positive exponent by just rewriting this as 1 over. Here's the x to the third that was in the denominator. And now this whole thing is going to become 5x to the negative 2, y to the positive 4, and it's all going to be now raised to the positive 1 power, which is convenient because I don't have to do anything with that. Everything's to the positive 1 power. So if I write this without the parentheses, it's 1 over, I have an x cubed, I still have this 5, I have an x to the negative 2nd power, and I have a y to the positive 4. Now these guys I can combine, right? If I have x to the negative third, x to the third and x to the negative 2nd power, that's just x. So if I write that out as these are just x together, this becomes 1 over 5. I've got my x, and then I've got my y to the 4th. Part C. Oops, too far. Part C, just a quick application of the distributive property here, makes this 2a squared plus an a. And I'm tempted to just not write that again, but I know from experience it's so much more helpful if I just take the time and rewrite this. It's very mellow, very relaxing. Just let the pen do the work. Now if I can focus on my like terms here, I can see that I have 2 terms that are squares, and then I have 2 terms that are just a to the first, and then I've got this one oddball b term. So combining like terms, I have 1 plus 2 more, so 3a squared. And then I have plus 12 plus 1a, which is plus 13a. And then finally I have the plus 7b. So there's that. D, I'm raising this entire fraction to the fourth power. And I've done this twice. I've done it two different ways. On the answer key that I posted on Aries, I raised everything to the fourth power first. But let's be honest, it will be much more simple to deal with if I go ahead and simplify what's inside of the parentheses. So I'm going to rewrite this as 2, and then I'll say this is a to the third, and then a b. And in my denominator, I have b to the negative third, a to the third. So I'm just going to pause there for a moment. This is still all raised to the fourth. If I look at this, you can see that I have a to the third appearing in both my numerator and denominator, and they are factors. So I'm going to cancel this common factor. Also, these three factors of b are in the, I guess I could say they're in the wrong location, right? 1 over b to the negative third is just b to the third. So I can rewrite this now as 2b times b to the third. You can see the 1b that was in the numerator, still all raised to the fourth power. I'm going to take this one more step. This is going to be 2b to the fourth power, raise that to the fourth power. And what this means, of course, is that I have exactly 4 factors of 2b to the fourth. And the shortcut way of dealing with that is it's 2 to the fourth times b to the fourth. 2 to the fourth is 16, and b to the fourth we will write as b raised to the 16th power. So this is my final answer. And if you're struggling with that, go ahead and just take the time and write out 2b to the fourth 4 times, because you have exactly 4 of those factors. And when you write it out, look at it, verify, you're going to get exactly 16b to the 16th power. Right, E, I have only this thing in the parentheses being raised to this second power. The 3 is not, so I'm not going to square the 3. I do have this x to the third that I can move up to the numerator. And I think I'm going to start that way. I'm going to rewrite this as 3, and then I'm bringing up that x to the third that was in the denominator. And then in my parentheses, I'm going to go ahead and raise the x squared y to the third all to the second power. So this is going to become an x to the fourth and a y to the sixth power. And then down below, I still have a y to the sixth power. Well, that's convenient. When I look at this, because I have y to the sixth power occurring as a factor in both the numerator and denominator, we can eliminate that common factor, and we're left with 3 factors of x and 4 more factors of x, which combine to give me 7 factors of x. So this is 3x to the 7th power. Whoops. Nearly done. So this next question says, write the rule and sketch the graph for each of the parent functions. So a constant function, the rule is f of x equals some constant c. And I don't know what the c is, but for example, if it was like positive something, it could be up here somewhere. That would be the parent function of a constant function. And this line can go up or down depending on what value of c is. The parent function for all linear functions is f of x equals x. And that's this nice little, got to go right through the origin, because when you put in 0, it gives you 0. Any value, if you put in 3, for example, if you put in 3 into this function would give you 1, 2, 3. So getting the same thing out of it. Quadratic parent function is f of x equals x squared, which is a nice little parabola that's just touching right there at the origin. My cubic function is f of x equals x to the third power, which is looking like this. And then finally, the square root function would look like f of x equals the root of x, principal root of x, and that function would look something like that. So those are my parent functions and their corresponding graphs. Next question. Identify the parent function of x minus 4 all raised to the third power. For question 11, I wanted to use my virtual TI to show you the graph of that, but on this little screen I can't make this calculator go up and stay, so I can't even turn it on. I push it up and it falls back down. But that's okay. I don't need the calculator for this. It's clearly a cubic function, right? So if I'm thinking about this, I know what those parents look like. It's like this kind of thing. Then the question is, I'm not adding something or subtracting something from the cubed part. I'm subtracting 4 from this argument inside. And the question is, oh, where'd that axis go? I don't know. The question is, did this thing get pushed to the right, or did it get pushed to the left? So I want you to think about this. On the basic curve, right, of the basic cubic parent function, I know that when I put 0 into it, it gives me 0. So the thing I'm wondering is, what would x have to be in order for this to become 0? And the answer is it would have to be 4. If I plugged in that x was 1, 2, 3, 4, and I plugged that value of 4 into this function, 4 minus 4 is 0, 0 to the third is 0. So I know that this point is on the curve. So what's happened is I've taken the entire curve and I've pushed it 4 units this direction. So now instead of the y-axis being this point right through where this inflection point is, now it's coming in like here and here, and then it's coming up like this. So what I'm looking at now is it is the parent function is what? The parent function would be f of x equals x cubed, right? And what's happened to this parent function is I've shifted it 4 units to the right. So that's my story with number 11. Number 12. Oh dear. Let's see. I can't. The directions for this say that I need to essentially plot the data points, right? Plot the points, and then describe the parent function and the transformation that looks like it's happening to that parent function. So this is pretty straightforward, right? I hate to take your time here, but I've got the -3 and the +7 as one of my points. I've got the 0, x is 0 and y is -2 as a point. Looks like these points aren't in order. I've got +2 going up to +2. I've got 3 going up to 7. We have +1 going to -1. And we have -2 going to +2. And the last value in this table is -1 is going to -1. So I look at that, and not linear. If I tried to put a line, through these, it's definitely not an absolute value function. So I've got what I would guess is a nice little parabola moving through here. I'm just going to curve this parabola in through here. And the parent function of the parabola, we just wrote it on the previous page, it was f of x equals x squared. And I know when I have that, right, the parent function sits right there. It has its minimum at the origin, right? So 0, 0. This appears to have been shifted down by 2 units, right? So the entire curve looks like it was moved down 2 units. So I'm betting that the function represented by this data is f of x equals x squared minus 2. Now I can confirm that's the function by just looking at some of the inputs and outputs. So for example, if I consider -3, -3 squared is 9, and 9 minus 2 is 7. 0 squared is 0 minus 2. 2 squared is 4, and 4 minus 2 is 2. So, certainly for these first few values, this is fitting quite nicely, and I'm pretty sure that's what the function is. Hey, anyways, guys, I hope you have a restful time, and just, shake it off, do your best prepping for the test. The more you prepare, you're going to find that the better you're going to do. So I look forward to seeing you on the test day on Friday.